group 1, 2, and aluminum have +1, +2, and +3 respectively. Last but not least, the sum of oxidation states or oxidation number of all atoms in a polyatomic ion equals the charge of the ion. Let's take a look, for example. Think of bicarbonate, HCO3 minus, right? Oxygen is the most electronegative, that's -2. Hydrogen we know is always +1 since it's not connected to a metal. And then that means carbon is +4. Okay, so 4 + 1 is 5. There's 3 oxygens, that's -2 times that, so it's -6. So -6 + 5 gives me a -1 overall charge for that bicarbonate. Okay. So the sum of oxidation numbers of all atoms in a polyatomic ion equals the charge of the ion. All right, so let me know if you need me to go back to the previous page. It's quite a lot. Got to remember our rules. Okay. +4. Oxygen was -2 times 3. That's equal to -6. Hydrogen is +1 by definition because it's not connected to a metal. And carbon then has to be whatever adds up to it to give it a -1 charge. So in this case, that's 4. 1 + 4 is +5, -6 is -1, right? -6 + 4 + 1 equals -1, which is the charge on our polyatomic ion. Okay. All right. So let's give you guys some problems for thought. Find me the oxidation numbers of each of the atoms that are indicated. If it's not indicated, then find me all of them. So practice problems. I'm going to call these problems for thought. Just getting you guys thinking about oxidation numbers again. First one, we have titanium hydroxide. We'll call that titanium hydroxide 2. Second one, an organic molecule. Find me the oxidation number for those carbons. Third one, sodium borohydride. It's a good start. So find me the oxidation numbers for the titanium, the oxygen, the hydrogen, and the titanium hydroxide. find me the oxidation numbers for the carbons in your organic molecule here. In this case, it's carboxylic acid, or actually it's just ester. Yeah. Ether. One of those. And then you have your sodium borohydride. Of course, periodic table is always available to you. But you should know the oxidation numbers and the relative charges on them. If you think about it, you should, based off of the periodic table of the elements and where they're positioned, right? From what we talked about from our first lecture. Your periodic motion, periodic in electron theory. So figure out what's the most electronegative atom. Remember, carbons bound to carbons don't actually give off any electronegativity. There's zero, the electronegativity difference between them. All right, so let's look at problem 1. What's the most electronegative atom in that element, or in that ionic compound? Titanium, oxygen, or hydrogen? Oxygen. What oxidation number should it have? What oxygen state? -2. Good. That means hydrogen is what? +1, because we know that hydroxides are -1. That means titanium is what? We have 2 negatives, then careful, Charo. This is only going to be +2, right? Because you have 2 hydroxides. All right, let's take a look at your second element. Let's look at the first carbon. That's connected to just 2 hydrogens and the other carbons. What's the oxidation number on that carbon? Remember, there's a hydrogen here and a hydrogen here, right? And we know that hydrogens are +1s. So that oxygen has a -2 oxidation number. Careful, right? The other ones are connected to carbons. Carbons connected to carbons have no electronegative pull, so therefore it won't change the oxidation state. Does that make sense, Eric? Cool. Sure. Since it's connected to hydrogen, and we know hydrogen has a +1 charge when it's connected to anything other than a metal, that means that the carbon had to have a -2. This also explains why, if you think about it, when you guys do your organic chemistry, why none of these carbons get attacked, or they're rarely attacked, right, by electrons. because it has a -2 oxidation number, which means it's already pulling electron density towards itself. Likes repel likes. What about this one? The other indicated carbon, the anomeric carbon. Yes, it's pulling electron density from the hydrogens, correct. Everyone always thinks it's +4. Careful. It's -1, -1, -1, -1. So it's actually -3. This oxygen is pulling electron density 1 negative for each one of these that are attached to it. So this side has an electron pull of electrons pulling this way of -1, and this one has a -1. And same thing with this oxygen. It's -1, -1. So leaving this to be -3, +3, not +4. Now, if it was only connected to the oxygen, if it was like the carbon was connected to the oxygen, like in carbon dioxide, then it would be +4. But since it's connected to another carbon, this is neutral out of the 4 bonds it has. So you think about it, where do the electrons from your nucleophilic attack for SN1, SN2, where are they most likely to attack? At the carbon that's -2 or the carbon that's +3? And this is why organic chemistry makes sense. When you're attacking, you always attack the anomeric carbon because that carbon naturally has a +3 oxidation state. Oxygen is -2, correct, Monica? It's -2 here, and it's -2 here, right, for its oxidation number. But since that oxygen is connected to 2 different carbons, sure, give me a second about that. Let me finish explaining this. So since that oxygen is connected to 2 different carbons, it's going to pull electron density from each one pulling roughly an electron away, right, or a -1 charge away to give its own -2. It'll make no sense that it pulls 0 from here and 2 from there, right? It won't pull 2 negatives from there when it can, because that'll just rip the bond apart. Does that make sense? So it's going to pull 1 and 1 from each one of those carbons that it's connected to. That's why this carbon that's here, oh my gosh, I had it on erase mode. Well, that's why this carbon here is going to feel -1, -1, and -1, which gives it a +3 charge. And since it's a +3 charge, that's where your nucleophilic attack generally goes, right? Think of like your rotations for your rings for glucose, right? Where do you usually attack or open up and form the ring from a straight chain to a chair conformation for glucose, right? It attacks at the anomeric carbon, right? So that carbon is the most electropositive, right? That's why electrons want to attack there. Does that make sense? Otherwise, you wouldn't see it, right, attacking at the other carbons, right? All these, because you think about it, you're always asking yourself, like when you were taking organic chemistry, right? Why wasn't it attacking here, 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 right? And all those other carbons. Those are all carbons, but look at those, look at the electronegativity on them and the actual oxidation numbers they would have. They all have -2 except for this one, which is a -3. Do you think electrons like would want to attack there? No. Any element bound to itself is going to be 0. It's not just always carbon, carbon, Alexandra. This is organic chemistry, right? You think of orgochem, you think of biochem, right? Biochem is what? Application of OChem. But yes. So this oxygen on top is taking a -1 and a -1. So that's -2. And this oxygen is taking one more. So that's why it's a +3 on this carbon. Yeah. There's no overall charge, right? Remember, these are all dipoles that we're talking about here, right? This is electronegativity pulling electron density towards itself. These are all creating dipoles. Correct. Each electron withdrawing bond with oxygen is a -1. Cool. All right. Now let's look at the sodium borohydride. So now we know that the hydrogen is attached to a metal, right? Boron is a metal, right? It's column 3, still part of metals. So what's the charge or the electron, the oxidation number for hydrogen? So Eric, if we go back and look at rule for hydrogen, rule 5, hydrogen is usually +1 unless combined with a metal, the metal hydride, which makes it a -1. So since there are 4 of them, it's going to be -4, but then we can always multiply, right? You can totally see that, but it's just a -1. What's sodium? So sodium is what? Alkali metal, so it's +1, right? Group 1 element. Good. So that makes boron what? Correct. +3. And all of these have to add up to whatever the charge is for that molecule. Since this sodium borohydride has no charge, it has to be a +3 oxidation state. Cool? So the reason that we're spending so much time doing this oxidation numbers and figuring out oxidation states, because that's the first step of balancing a redox reaction, right? We need to know what the oxidation states are on each of the metals to figure out how much they've gained and how much they've lost in terms of electrons, okay? When you're reacting them. Yes, I personally like remembering these 7 rules because they pretty much cover everything that you need to know in terms of figuring out oxidation states and oxidation numbers, right? So let's do some little bit trickier ones. So let's do some dichromate, Cr2O7, 2 minus. Let's do some phosphate, PO4, 3 minus. Yeah, that should be good. So let's look at dichromate. This is a polyatomic ion. We're looking at rule 7 here. Still have to use all the other rules. So the most electronegative atom or element in dichromate is oxygen. So oxygen has what oxidation number? It's not connected to fluorine. It's not connected as a peroxide. -2. Very good. And there's 7 of them, so that's -14. You're going to have a -2 overall, so that means chromium has to have a +12 charge, right, out of the 2. So that means the oxidation state of each chromium is what? How much? Very good. +6. 6 times 2 is 12. -2 times 7 is -14. So +12 minus 14 gives us an overall charge of -2. Easy? Just getting you guys thinking about it. Let's look at phosphate now. PO4, 3 minus. So oxygen is what oxidation number? Still -2. So what's phosphorus? Correct. This is a binary compound. So that's -8. So that means, and then you have to get a -3. So this has to be +5. Remember, +5 minus 8 has to equal to -3, right? So this has to be +5. Simple math we're doing here. Got to keep up with the arithmetic. So far, so good? Yes, the +6 is for each chromium atom, not for both. It's +12 for both. Kayla. Awesome. Phosphorus, P? I thought that was, okay. 5 plus, 2 minus, right? Excellent. So now that we know that, now we get to look at balancing redox reaction. So let's look at the rules for balancing redox reaction. So balancing a redox reaction, the first one is to determine the oxidation states of all the atoms during our redox reaction. 2, identify the number of electrons transferred in the oxidation half reaction and the reduction half reaction. Third, balance the electrons by finding the least common multiple. The LCM, least common multiple between the number of electrons transferred. Fourth step, balance charges on each side by either adding H plus or OH negative based on acidic or basic environments. And fifth one, last but not least, we balance atoms by adding water to the appropriate side of the reaction. So these are the 5 steps, kind of like my forced problem recipe. These are the 5 steps I use to balance redox reactions. Determine the oxidation states of atoms. That's what we were practicing earlier. ID, the number of electrons transferred in the oxidation half reaction and the reduction half reaction. 3, balance the electrons by finding the least common multiple. So you're going to multiply them so that you get to the least common multiple. So you transfer a equal number of electrons for the oxidation and reduction half. Number 4, balance charges on each side by either adding H plus or OH minus based on acidic or basic environments, and balance atoms by adding water to the appropriate side of the reaction. Okay, so let's practice this and balance our redox reaction. So those were practice problems. This is like the real beginning of redox, right? So we're going to look at bismuth oxide minus, and it's aqueous, means it's dissolved in solution, plus manganese ion, aqueous. That's going to become bismuth 3 plus, aqueous, plus permanganate, MnO4 minus, aqueous. And I'm going to tell you that we're in a acidic environment. So use these steps to balance it. So find the oxidation state of every atom. There's 2 ways to do it. One is the half cell reaction. The other is the bridge method. I'll show you how to do the bridge method first. I personally like the bridge method over the oxidation half and the reduction half. Teachers always made you do the oxidation and reduction halves because it shows you where all the electrons are and how they're getting transferred so that you can cancel them out. But I personally like the bridge method because when you find the LCM, the least common multiple between them, you're naturally canceling out the number of electrons transferred at that point. So that's why. I'm going to go over the bridge method, and then I'll go over the half cell method, how to balance your oxidation reduction reactions. Gotta try doing it yourself. Let me know when you guys get the balanced chemical reaction. I believe there's a mailman at the door, but yeah, you can think that, Sophie. Yeah, I believe we're getting a package delivered, so he kind of loses it every time there's a mailman coming to the door. Apologize. Magnesium starts off as 2 plus. Okay. Seeing that there's a lack of people jumping to give answers, let's go over each of the steps. Yeah. So usually somewhere along the way we got stuck, right? Because there's a lack of answers. Somewhere that happens. So let's identify and figure out how to do it each step along the way. So step one, let's determine the oxidation states of the atoms. We know oxygen is -2, and there's a -1 overall. That means bismuth starts off as what for its oxidation state? Positive what? Good. Excellent. Now, let's take a look at manganese. Permanganate. So this is oxygen's -2, right? And that's -8. That's -1. So manganese has to have what for its oxidation state? +7. Oh, look at that. Went from +2 to +7, and it went from +5 to +3. So we gained 2 electrons here, because +5 add 2 negatives give you a +3. And over here, we went from +2 to +7, so we lost 2 electrons. Correct? Sorry, 5 electrons. No, just the electrons. Hydrogens, we'll use that to balance out later, Michaela, but we're not saying that we gained 5 H pluses, because there's no, we wouldn't balance out this reaction because you're adding in hydrogen atoms all of a sudden. So be careful when you say that. Just transferring electrons here. So that we did step 1. We determined the oxidation states. Step 2 was identify the number of electrons transferred. So bismuth is getting reduced and manganese is getting oxidized, correct? So this is my bridge method. The third step was balance by finding the least common multiple. What's the least common multiple between 2 and 5? 10. Good. Which means we're going to have to multiply all the manganese terms, or the elements that have manganese in them, by a factor of 2 to get 10. And we need to multiply the things that have bismuth in them by a factor of 5 to get 10 electrons transferred. We're good here? Step 3, totally fine. So I did step 1, step 2, and step 3. So 2 atoms of manganese converting to 2 atoms of +2 manganese to 2 atoms of +7 manganese is 10 total electrons transferred. This way I don't have to worry about tabulating up the electrons like you do in the half reaction. Okay. Correct. You add the 2 and the 5 respectively to both sides of the reaction. Now let's balance the charges. So we know it's an acidic environment, so we can only add what? H plus. So where are we going to add? So let's take a look at the charges. So we have -5 here. We have +4 here, because there's two pluses. We have +15 here, and then we have -2 here. So on the right-hand side, we have +13. On the left-hand side, we have -1. So where are we going to add hydrogens, and how many, and to which side? Correct. Someone mentioned that we're going to add it to the left side because we're going to add how many to the left side? Correct. We had a student question what I was doing here. How did I get the -5? This is 5 bismuth oxide, so this is a -1 charge, so that's why it's -5. There's 2 positive 2s here. That's how it becomes a +4. So on the left side, it was -1 charge. Does that make sense for the student that asked me? We'll do atoms at the end. We reconcile atoms at the end. Someone asked, why is it -2 for permanganate? Permanganate has a -1 charge, and there's 2 of them. Hence, -2 charge. Right? Bismuth, 3 plus, has 5 of them. Hence, +15 charge. Cool. Good. So now that we have that, we're going to add, a bunch of people said in messages, 14 hydrogens to the left side. So let's rewrite our problem. So we have bismuth oxide, 5 of them, plus 2 Mn2 plus 14 H plus becomes 5 bismuth trication and 2 permanganate ions. Okay. So now we've balanced and we've got up to step 4. Let's go back. From the previous step, this side has a +13. This side is a -1. How many, and I can only add H pluses. How many H pluses am I going to add to make these 2 sides have the same charge? Yes, 14 minus 1 equals 13. Thank you, Sarai. Cool. So now we're here. Now, one of the students that wanted to balance the atoms, now we can balance the atoms. Okay? This is the last step, balancing atoms. So if you think about it, bismuth, we have 5 on the left, 5 on the right. Manganese, we have 2 and 2. Hydrogens, we have 14. This side we have 0. Oxygens, we have 15. And over here, oxygens, we have 8. Right? This is hydrogens. This is oxygen. This is 0. Sorry. Differentiating between the 2. So the last step is what? We're adding water, right? H2O. You look at our last step. Balance the atoms by adding water to the appropriate side of the reaction. So how many waters are we adding into which side? To the left side, we have 14 more hydrogens and 7 more oxygens, right? That makes perfectly, like Glenn said, 7 waters. Okay. So we end up just adding 7 waters. And now all we have to do is place in those aqueous for all these ions that are dissolved in solution. And now we have a perfectly balanced redox reaction. Cool. So if it was in a basic situation, we can only add negative charges by adding OH, yes. So then in that case, we'd added negative charges to the right side to make it -1. Does that make sense, Michaela? I was asked to go over step 5 again. Ugh. Yes, I understand that it was an if. I do that typo all the time. Okay, so step 5. Before we added this water, if we looked at the bismuth, there were 5 on the left, 5 on the right. We looked at the manganese, there was 2 on the left, 2 on the right, respectively. We looked at the hydrogens. This one had 14, this has 0. And if we looked at the oxygens, this has 15, and this has 8. 2 times 4 is 8, 5 times 3. This 5 times 3 oxygens gives me that 15 number. This 2 times 4 gives me that 8 number. If that's the confusion part for the student that didn't get where those numbers of oxygens came from and the numbers of hydrogens came from. Numbers of hydrogens were easy, they're right here. Excellent. What's the difference? The difference was 14 hydrogens and 7 oxygens. Sorry. Students were messaging me, how did we get 7 from that? I was like, how much ratio of that of H2O can we make? Right? We have 7 oxygens. I think there's going to be 7 water molecules, right? And there's exactly 14 too, which makes it so perfect. Sorry, there was a question about why we need to count electrons and can't just balance normally. Because with redox, you need to make sure that the number of electrons transferred is correct. That's why we did step 3, going back over here. Step 3 was super important to balance the number of electrons. So when we multiplied this by 2 times 5, that's 10 electrons. And 5 times 2, that's 10 electrons. So bismuth had gained 10 electrons and manganese had lost 10 electrons. Other regular reactions don't transfer electrons. Think of acid-base chemistry. There's no electrons that are being lost or gained. Your oxidation states stay the same. And acid is always protonated and then reprotonated. Look at any other chemical reaction that you've done, the oxidation states stay the same. So in that case, you're not losing electrons. That's why it's different. Doing redox is different from doing any other chemical reaction that you have. Leandro, you sorry. I was just looking at the thing. I have a bunch of messages coming in from different people. And yeah, sorry. So we had a question come in. Do redox usually involve transition metals? And is the reason for the varying oxidation states beyond what we expect? No, the varying oxidation states typically fall in the range that you've already gone over before. when you did your polyatomic ions and when we talked about ionic bonds in physical chemistry. The reason that we like using transition metals is because they have a lot of electrons to lose, right? You think about it. Besides column 1, column 2, I mean, what other metals do you have available to you, right? Your alkali, your alkaline earth, and your transition metals, right? Think about it. Most aluminum type things that are boron type things that are 3 plus are really rare. So, yeah, that's typically the case. Why we have a lot of transition metals coming in, because there's so many electrons for them to lose. And you're always bouncing back and forth these electrons from one state to the other, right? So one transition metal will gain it, one transition metal will lose it, right? And they can bounce back and forth and transfer those electrons with each other. Cool. So then that's how we got the 7. And then we are done with this redox reaction. Now let's do one other one. So second redox reaction. This one I'm going to do in the half cell method. Okay. So we have sulfur dioxide, aqueous, plus dichromate, aqueous, becomes sulfate, 2 minus, aqueous, plus chromium 3 plus, aqueous. And we're all in acidic conditions. So we still do step 1 and step 2 the same. Still write the oxidation numbers for each of the atoms, figure out what's gaining, what's losing. Then we write them in the half cell oxidation half cell reaction and the reduction half cell reaction. We'll do both methods. I personally like bridge because I like seeing all of it at once, but it's not necessary. You can do the bridge method if you like to. If you find that that works for you, feel free to do it. We're just trying to give you options on how to approach balancing a redox reaction. Because the end goal of all of this redox is to eventually put it used to it in terms of a battery, right? Because all of this will end up giving you an electric potential, and then that electric potential can be used to drive electric circuits and give you electric current, right? Because the movement of all these electrons is where current comes from. So I just wrote the oxidation states if you're still struggling. I want you guys to try to do this on your own. Part of this time that I'm giving you in class isn't just to waste time. You actually have to develop those neural pathways in your brain so that you can do this on your own. And that when you get into test day, you have confidence that hey, if they give me any weird redox reaction that's occurring, I know that I can balance that redox reaction that they give me. So that when it comes into, a biological application for electrochemical cells, and so you can know what number of electrons are being transferred. Okay. Let's take a look. So we know that sulfur here went from being a +4 to a +6. Did it gain or lose electrons? How many? So sulfur in this case got oxidized, correct? And chromium went from being +6 to +3. This one gained, so this got reduced. In this case, it gained 3 electrons. Okay? So we've done the initial part the same, right? So now let's write each of our chemical half reactions. So the oxidation half is going to look like so. We have sulfur dioxide, aqueous, is sulfur sulfate plus 2 electrons, right? Because it lost 2 electrons. So electrons are in the products now. For the reduction half reaction, you have dichromate becoming chromium 3 plus ions. Let's balance out those atoms first. There's 2 chromiums, there should be 2 chromiums. So it gained 3 electrons, but realistically, there are 2 of them, so you actually gained 6 electrons. It's 3 for each atom, right? And then since there's 2 chromium atoms, you gain a total of 6. So this is the number of electrons that we see being transferred. So what do you do with the LCM? So I personally like to balance the redox reactions first using charges, using atoms, and then I'll multiply by the LCM using the half cell method. Okay, so it's a little bit out of order from the order that I gave you. So we did step 1 here. Step 2 we did here. So instead of doing step 3, I wrote the half cell reactions. This is all part of step 2. And I'm going to do 3 and I'm going to do 4 and 5 real quick. So what I'm going to do is I'm going to balance each one out. So my oxidation, I'm looking at charges, and I can only add, so this side has -4 charges. Remember, the electrons count as charges. On the right side, there are no charges, so I have to add 4 hydrogens. So you see? -4 plus 4 gives me 0, which is what the charge is on the right-hand side, left-hand side. And then now we have 4 waters, 4 hydrogens, 4 oxygens, 2 oxygens here. So we're going to add 2 waters here. This was step 4. This was step 5. Okay. I'm going to do the same for chromate, dichromate. So we have 6 electrons, -2, so that's a -8. And on the right side, we have a +6. So we need to add how many hydrogens to balance out the charges. This is +6. This side is -8. So how many hydrogen pluses am I going to add to the left side to make it +6? Or you think about it, -8 plus what number gives me +6? Some number plus this is equal to +6. Correct. So you're going to add 14 hydrogens. That'll balance out the charges. And then we're going to balance out the waters. This side has 7 hydrogens and 7 oxygens, 14 hydrogens, 7 oxygens. We're going to add 7 waters again. So let's take out all this stuff. We just did step 4 and step 5. Now we're going to do step 3, the least common multiple. So we're going to have to multiply one of these. So what's the least common multiple between 2 and 6? Least common multiple between 2 and 6, everyone? 6. Good. Simple enough. So that means we do nothing to the reduction half reaction, and we multiply the oxidation half reaction by 3. So we're going to get 3 SO2 plus 6 H2O, right? we're going to get 3SO4 2 minus plus 6 electrons plus 12 H pluses. On the reduction half, we're going to have dichromate plus 6 electrons plus 14 hydrogens. On the right-hand side, we're going to have 2 chromium ion 3 pluses plus 7 waters. So we notice that the electrons will cancel out. We notice that we're going to cancel out all but 2 of the hydrogen pluses. And there's 6 waters here. We're going to cancel it out so it only has 1 water left. Okay. And then you just basically do this like you would a mathematical equation. We just add down. So left-hand side, we have 3 sulfur dioxide plus dichromate ion plus 2 hydrogen pluses. Then we're going to be left with 3 sulfates plus 2 chromium 3 plus cation plus 1 water. Now we have a balanced reaction. Left side, all the atoms are balanced, charges are balanced. Correct. I gave you the option of doing it both ways. When you guys did this in high school, I'm pretty sure your teacher made you do this way. We call this the half cell method. So this method is called the half cell method, where you work on each one completely. And the one that I did previously, this was called the bridge method. Okay. Both are discussed in the book. You can choose either one to do to figure out your oxidation and reduction half cell reactions, okay, to balance out your redox reactions. Any questions? Good. Now let's talk about electrochemical cells. Oh, they'll give it to you as like multiple choice. We can look at it during office hours if we have time. Today we'll go try to look at some problems, but you have to do it fairly quick. It's not like something that's going to take a long time. Usually they give it to you and you have to figure out, they'll ask you what's the oxidizing agent, what's the reducing agent. Oxidizing agent is the thing getting reduced, the reducing agent is the thing getting oxidized, right? So we just have to make sure that we know how, and then the ratio of each, they like ask questions with the ratios of each. You see that in your in-class questions that Todd gave you the packet to, okay? So first thing, electrochemical cells. So we're going to figure out how batteries work. It's exciting. We're going to take that redox that we did and figure out how batteries work. So we're going to take the voltage of a cell is simply the oxidation potential plus the reduction potential of your reactions. So the values for these are derived from tables. The other equation that we need to know, so they'll either give you all reduction potentials or all oxidation potentials. And you can tell easily, right? If the electrons are on the reactant side, it's the reduction potential. If the electrons are on the product side, it's the oxidation potentials. Okay. The other equation, so this equation is important to figure out the voltage of a battery, the oxidation plus reduction potential. The next is the Gibbs free energy, the delta G of a reaction is equal to negative of Faraday's number of electrons that you're transferring in the reaction times Faraday's constant times the electric potential of the cell. Okay. Where N is equal to number of electrons transferred per reaction, and F is Faraday's constant. That's equal to 9,600,500 coulombs per mole. Okay. So for electrochemical cells, there are two types of cells that we need to know. Let's take a look at those two cells. No, it's the number of electrons that we found, like when they're transferred using the oxidation states, Aditya. Yes, I can go back. Not a problem. $96,500. Cool. So there's two types of electrochemical cells. The first is a galvanic cell. This is your typical battery. The cell is spontaneous, right? You plug and play. Are the constants usually given? Typically, they expect you to know the constants. Especially if I'm giving them to you in class. They've come up before where they did not give them. Okay. Student asked if we had to know these constants. Yes, typically, if I'm giving them to you in class, it's come up before where they are not given to you. So that's why I'm giving them to you now. Good question, though. Yes. For the most part, they like to give them to you, but I rather be safe than sorry. So galvanic cells. Cool thing about galvanic cells, they're spontaneous. Gibbs free energy is negative, right? That means what? Spontaneous. That means this chemical reaction is going to occur, right? And the cool thing about it is the voltage of the cell from the battery is always going to be positive. These are all your batteries that you use, right? Your AA, your AAA, your 9 volts, those flat batteries that you use for watches, whatnot. These are all called galvanic cells. So let's look at the characteristics of a galvanic cell. There's 2 chambers on either side. You can see this in the handout as well. If you want to follow along in the handout, it's pretty analogous to that. There's usually some metal here. It's connected to another metal on the other side. These are always in solution. These are always in solution. And then so it's usually some type of metal. So one side is going to be the anode. One side is going to be the cathode. So whenever you see the anode, this is where oxidation occurs. That means we're going to be losing electrons from there. Whenever we see the cathode, this is where reduction occurs. So let's say we have zinc and copper battery, okay? So let's say this side is zinc. Zinc metal is going to become zinc 2 plus 2 electrons. So what ends up happening is that zinc metal becomes zinc 2 plus in solution. So it gets smaller. So that plate dissolves, right? It looks like it dissolves. The reason being is the electrons that it gives off are being sent across there to the other plate. Over here, that copper that's in solution is going to combine with those 2 electrons that are coming in to make copper metal. This is the reduction part. So then you see this plate get fatter, right? Same thing happens in your phone, right? If you plug in your phone and leave it for so long time and over a long period of years, you can see that that phone gets a fat battery. Same thing. Too much oxidation, a reduction that's occurring on one side over the other. Yes, zinc is the reducing agent and copper is the oxidizing agent, right? Or copper 2 plus is the oxidizing agent and zinc metal is the reducing agent, right? These are your reactants. These are your products, right? Products. These are the reactants when you do a redox together. So when we wrote redox, we write them all together, right? We don't separate it into your half cell reactions like we did here, unless you're using the half cell method. So eventually, this is going to cease, right? Because you can't keep on putting negative charges into one side over the other. Sure. There was a request to go back one slide about electrochemical cells and the 2 equations that we needed. The oxidizing potential and the reduction potential. So in your handout, there's a table of standard reduction potentials, or they'll say there's a table of standard oxidizing potentials. They'll have to give you that on the MCAT. But to find if they give you one, to find the other, you just simply reverse the reaction and change the sign. Okay. And then delta G is your Gibbs free energy. Cool. So the cool thing about your galvanic cell, since it's spontaneous, that electric cell potential is positive, right? So if we look at the table that you guys have in your handout that you guys can look at or download from the courses or handouts website, or the handout section on our website through the portal, you'll see that zinc has an oxidation potential of 0.76 volts and copper has a reduction potential of 0.34 volts, right? So the voltage of the cell in this case is 1.1 volts when we add those 2 numbers up. And those are derived from the tables. So most batteries have what we call a salt bridge that'll take, oh my gosh, I hate when I do that. That'll take ions back. So this is called the salt bridge. That'll take ions back. So negatively charged ions like chlorine will go across here so that the flow of electrons will continue endlessly until you eventually run out of zinc metal and have all zinc solution, and you have this fat plate of copper metal, okay? Because electron repulsion will finally take over if you keep on sending negative charge to one side and not sending it back. So that's what the salt bridge is doing. It's allowing that negative charge to go backwards, okay? Realize that electricity is the flow of electrons, not the flow of protons. So when we talk about current flow in physics, physicists call electricity or current the flow of protons. And you're going to be like going like, no, it's not. Yeah, that's the one difference between chemistry and physics. Chemists chose electrons before they knew what an electron was, besides that it was negatively charged. Physicists chose protons, and so their derivation of current or movement of charges is vastly different from each other, but that's the only thing. Okay, so it's really easy to remember. Current in chemistry flows alphabetically from anode to cathode, A to C, right? So really simple and quick way to remember. So this is your galvanic cell. This is your typical battery, okay? So eventually your battery dies out, right? Because you run out of material to grab electrons from, right? That zinc gets finally dissolved and becomes all zinc ion, right? In solution. And then it's like, well, no more zinc, no more chances for us to get electrons in solution, okay? So the next one that we're going to look at is what we call an electrolytic cell. I like to think of it as looking at a chemical reaction and seeing if we can reverse it. The electrolytic cell it's their solution. It's just not like physical, like it's all enclosed in the battery, right? It's just not a giant vat of containers of like solution that you think of. Yeah, it's all contained within the battery. There's solution in there. So that's why when you puncture a battery, or like if you drop it really hard, like you get battery acid leaking out. And over time that solution dries. Like I'm sure you've had this with like old batteries, right? That you've never played with your toys for a while, like RC remote control cars or something, or like those like typical like music playhouses or a music box. If you leave that battery for a long period of time, there's that like salt that dries up, right? Yeah, that white stuff. Yep. Kayla knows what I'm talking about. That's the leakage of the battery, except what happens? They're full of salts, right? So what happens when salts dehydrate or dry out? They leave salt crystals. That's what you see. So your battery has a solution. Double A, triple A, all of them. They all have solution in them. It's just, how much do we have dissolved in solution from all these salts? That's why I wanted to teach solubility. Now I'm teaching this because all those ions that we're talking about is dissolved in solution. That's why aqueous means, right? So neither. Good one, Noah. Neither. I don't think you like eating metals outside of the alkaline earth, right? So you want to eat metals that exist in your body, right? Think about it. So what's in your body? Magnesium, potassium, sodium, and I believe that's it. So when you think of like those Gatorade drinks and stuff like that, where it tastes metallic, those are the ions they have dissolved in solutions. And you have chlorine, obviously, right? But yeah, so those are what you want inside your body, Noah. Like the ones from batteries, we're going to be dealing with zinc, copper. I don't know, like those just don't sound like something that you want in your body. They might actually mess up the electrochemical processes because they're either too electropositive or they have too much electrons and they can actually, yeah, probably not a good idea. Yes, change it up. Not a good idea. But yes, I was like, yes, the salts exist. You've seen it. Like these are all things like you've seen. That's why I'm like, I love teaching physics. I love teaching physical chemistry as well, because these are all things that you've experienced and seen in real life. Okay. So for the electrolytic cell, this is a non-spontaneous. Delta G is greater than 0, right? So this is non-spontaneous, so not favorable reaction. So it's not going to go, right? It doesn't want to discharge. And the electrochemical cell, the voltage of the cell, is a negative number. That's how you tell, right? Either you look at the Gibbs free energy or you look at the electric potential of the cell, it's not going to want to go. So let's say it's the fully reaction that we just went over, except now we're trying to change it so that that copper wants to discharge. So the copper that was fat here to begin with that we made from the last one, and the sliver of zinc that we have left over here. Except now what's happening is we're changing the copper side to be the anode side and the zinc side to be the cathode side. So here we want the zinc ions that are in solution to gain those 2 electrons and become zinc metal. And on the anode side, we want that copper metal to dissolve and give off those 2 electrons. But if we look at the electric potential of the cell, electric potential of oxidation is negative 0.34 volts. And the oxidation potential of reduction here is a negative 0.76 volts. So the voltage of the cell is negative 1.1 volts. So it's not favorable. So how do we overcome that? So for electrolytic cells, we need to add a battery, an external battery, to drive the reactions and drive the electrons back to the cathode side of the reaction. So I think of the electrochemical cell as recharging my battery, right? So if you think about it, you discharge your battery naturally, right? It doesn't take any work. But then what do? You recharge it to get it back, right? This is when your battery's dead. How do you get those electrons to flow back? You hook up an external power source, right? You plug it into your charger, right? So that's what the charger is doing through the dongle. It's driving a voltage source to push a gradient of electrons back in the reverse direction that they were going before. So I like to think of the electrolytic cell as the recharging of that phone that you use every day, right? Because you're just bouncing it back towards that other side. And so over here, this becomes really thin again and then this begins to plate out and gets fat, right? Because reduction is happening here. And oxidation now is happening where you had reduction before. Super, super cool, right? So now you're talking about that whole discharging and recharging of that battery by putting an external voltage source in series with it to drive the electrons back in the reverse direction. Okay? So this is my example of the electrolytic cell and what's going on. So when you guys get these types of electrochemical cells on your MCAT, you end up getting this type of notation. Nothing. It's just a caret. Since they're not on technically the same line, I'll just erase it and write it as one external battery. There. It's just a caret symbol to insert things. Sorry. Someone asked me what was underneath external. I'll just, nothing. Oh, this symbol right here, that's electrons. It's just the movement of electrons. So we're driving electrons back. So electrons now want to move in this direction. And in this case, there were 2 electrons, right, that we're driving out and moving for your electrochemical cell. Cool. You're welcome. Okay, so when you guys get your redox type of reactions, the MCAT loves using this notation. So metal oxide, that's getting oxidized, that's a solid, single line, some concentration of that metal oxide. Now at some ion, let's say it's 2+ here, kind of like what we just did. And the other notation is some amount of some metal reduction. It's going to get reduced. And you form some metal solid, right? So this is the concentration of your ions that you have in your cathode that you start with. And this is the concentration of the ions that you have in solution from your anode that has been dissolved into solutions. So these still are reactants. These are your products, right? So that M can be replaced with any metal. So M's for metal. So it could be any metal that they give you, and it's always in this type of notation. So for this one right here, it would have been copper was what was getting oxidized. So it would have been copper S, 1 bar, some percentage of copper 2+, double bar, some percentage of zinc 2+, and then zinc solid. Okay, so this is how it would have been written. So this is the shorthand notation to say, hey, that's a redox reaction that we have occurring, and you need to figure out the oxidation potential, the reduction potential, and the electrochemical cell potential, or the voltage of that cell. Okay, and that just tells you the ideal voltage when it first starts. Okay, so now we're going to go one step further, and we're going to learn about Nernst equation and looking at the Nernst equation and how that voltage changes as this thing starts losing concentration, and as the anode starts losing concentration or gaining concentration in the dissolved metals that it has, and the cathode starts losing concentration in the dissolved solution that it has, okay? Because it's plating out on the solid, into solid form. So now we need to look at Nernst equations. So Nernst equations then allows us, so let's look at the derivation real quick. Sure, no problem. We'll go back 1 second. So this is the shorthand using that metal notation. So metal oxidized becoming metal ion. The other one is the reduced metal ion becoming metal solid, okay? So Nernst equations, delta G overall is equal to delta G at standard conditions. This is your starting conditions, plus RT, natural log of the reaction quotient. So reaction quotient is the ratio for terms in terms of products over reactants, but just not at equilibrium state. Okay, so it could be at any given state that this reaction is occurring. Now, if we substitute in for Gibbs free energy, we see that it's going to be negative NF V cell is equal to negative NF V at standard potential. So this is the voltage that you found using your oxidation and reduction potentials from the tables. They always have a little degree symbol over them. That just tells you that they're under standard conditions, standard temp and pressure. Okay. Plus RT times Q times the natural log. So this is the standard that we started with. This is the variation that we have as that battery begins to drain. And this is the overall voltage of the cell. So if we divide everything by NF, because those are basically constants, the voltage of the cell is going to be the standard voltage that you get from your calculations from the oxidation and reduction potentials minus RT all over NF times the natural log of the reaction quotient. Do some more mathematical manipulation. Voltage of the cell is equal to the standard voltage minus 2.3 RT all over NF. Now we changed it from natural log to log of the reaction quotient. And you will be asked to remember certain log values. And since we know the R is the universal gas constant, T in terms of temperature is your standard, room temp, and then F is your Faraday's constant. If we plug in for all those numbers, the voltage of the cell is equal to the standard voltage minus 0.059 all over N times the log of the reaction quotient. So R, let's put in the constant numbers that I talked about, 8.314 kPa times liters all over moles times Kelvin. Temperature is room temperature, which is 298 Kelvin. That's 25 degrees Celsius. And Faraday's constant, we already know, is 96,500 coulombs per mole. Okay. So we need to do some log review because you do need to know some log balancing things. So let's do some quick log review. You will not have a calculator. Okay, so log rules. Log base A of B is equal to C. That's basically A to the C is equal to B, going back and forth between logarithmic and exponential form based on that log. First rule we need to know is the power rule. Simply states that log of x raised to power, you can bring that power down and multiply it to that log. Product rule for logs, when you have log of A times B, that's simply log of A plus log of B. Quotient rule, log of A divided by B is simply log of A minus log of B. And there's certain logs that you need to remember. Log of 2 is 0.3. Log of 3 is 0.48. Sorry, not 0.5. To be exact, it's 0.48. Log of 5 is 0.7. Log of 7 is 0.84. And you ask me, well, you skip log of 4 and log of 6, right? Well, what is log of 4? Isn't that just log of 2 plus log of 2? Isn't that log of 2 times 2? So then you can write it as log of 2 plus log of 2. So log of 4 is 0.6, right? And log of 6 is just log of 2 times log of 3. So then that's just log of 0.78. Do you see? Power rule is you take this power when it's raised to an exponent and you can bring it out in the front. Let me know if you understood what I said. Cool. So this is how we use this log review. This is super powerful. So know this equation. You don't need to know all the derivation, and you need to know all these log rules. The reason being is you're not going to only use logs here for Nernst equations. You're going to use log again when we talk about sound intensity level, and you're going to use logs in acid-base chemistry. You're going to use logs in your titration chemistry as well, right? When you use Henderson-Hasselbalch with a buffer. So logs can be all over on your MCAT, from acid-base chemistry to electrochemistry to your sound and the Doppler effect. You're going to be using logs, okay? So know these basic log review. Like, I'm presenting it to you now. This is everything that you need to know to be successful whenever you're calculating these types of questions with regards to log, okay? So let's give you guys a question that encompasses this. So number 4 for the day. I want to know which of the following cells has the greatest voltage. So A, zinc solid, 0.1 molarity of zinc 2+ ion, double bar, 1 molarity of copper 2+, copper solid. B, zinc solid, 1 molarity of zinc 2+, 0.1 molarity of copper 2+, copper solid. C, nickel solid, 0.1 molarity of nickel 2+, 1 molarity of silver, and then we have silver metal solid being made, and D, we have nickel getting oxidized to get 1 molarity of nickel 2+, and you start with 0.1 molarity of silver at that point, turning into silver solid. So these are the concentrations of your solutions in each of the anode and cathodes respectively, right? It goes anode, then cathode, right, in terms of the notation. So if we looked at it from back here, this side was your anode, this side was your cathode in terms of that notation. And I'll go back to the problem. And this problem kind of encompasses all of it, right? Because balancing the redox, looking at the oxidation potentials for your zinc and your copper, understanding that we're balancing the number of electrons transferred Luckily here, we're transferring it from 2 electrons for each, and then 1 electron for C and D, right? So that changes your calculation. So this type of problem seems a little overwhelming at first. So if we think about it, for A, the voltage of the cell is equal to standard voltage for copper and for zinc, oxidation potential and reduction. You add it up, it's going to be 1.1 volts that we used in our example. Minus 0.059. We're transferring 2 electrons times the log of products over reactants, 0.1 over 1. For B, it's the voltage of the cell, which is 1.1 minus 0.059 all over 2 log of products over reactants. And this one is 1 divided by 0.1. Remember, products, this is a reactant, product, reactant for your anode, cathode, respectively. For C, the voltage of the cell, if you find that the oxidation potential for nickel from the table within your handout and the reduction potential for silver, and you add it up, it gets 1.03 volts minus 0.059. And we're transferring 2 electrons still. Log of products over reactants. V cell 1.03 volts minus 0.059 over 2 log of products, which is 1 over reactants, which is 0.1. So, correct. This is 2 plus right here. So it has to be 2 electrons that are transferred. Same thing here. It went from metal to being 2 plus. And this one went from being 2 plus to metal. And this one from going from being plus to metal. So that means 2 electrons maximally when we find the LCM are transferred for both all these types of reactions. Good. Nope, you made the observation. I'm just showing you where it is. So, and these numbers are derived from those tables, right? This 103 is the oxidation potential of nickel plus the reduction potential of silver, right? And that's how you got the 1.03. And we already know where the 1.1 came from. So we have to do the log. So log of 1/10 divided by 1 is the same thing as log of 10 to the negative 1. And that's negative 1 log of 10. So log of 10 is just 1, so that's equal to negative 1. So this value will make this added, right? Because it's just negative 1. And then log of 1 over 0.1. That just becomes log of 10, which is 1. So since it's 1, then you're just going to subtract. So you want the greatest potential. So we want the ratio of 0.1 over 1. And then when comparing, 1.1 is going to be larger than 1.03. So we're going to choose this to be our answer. Okay. All right. With that said, we're done with redox reactions and electrochemical cells. If you guys have questions, I will be having office hours tomorrow, Thursday, 11 to 1. I believe I sent an email out to everyone, and Josh has it now on the school portal when my office hours are. So if you have questions, feel free to message me and email me then. Otherwise, I will see you guys tomorrow. I can't stay after class today because I have another meeting that I have to go attend for work. Okay. But if not, I'll see you guys next week on Monday.